What if the ultimate cure for our planet's climate fever was a slow-acting poison for its very heart, the ocean? An ecosystem so vast and ancient it feels eternal, the cradle of all life on Earth. Imagine a revolutionary technology, hailed as a potential savior, one that could literally suck the carbon dioxide right out of the seawater that covers 70% of our world. Now, imagine the very same scientists who pioneered this breakthrough are the ones sounding a terrifying alarm. They are warning that their own creation, if unleashed on the massive scale required to save us, could inadvertently create invisible dead zones, starve the absolute foundation of the marine food web, and place an unimaginable, crippling stress on the ocean's delicate ecosystems. This is not the plot of a dystopian science fiction novel. This is the shocking and very real dilemma emerging right now from the United Kingdom, where a groundbreaking project is suddenly at the center of a monumental environmental controversy. Today, we are diving deep, far below the surface, into the turbulent and uncertain waters of a technology called direct ocean carbon capture and storage. We are going to unravel exactly how this incredible machine is supposed to work, expose the alarming potential side effects that have its own creators scrambling for answers, and confront one of the most critical questions of our era. In our desperate race to fix the sky, are we about to break the sea? In this investigation, we will explore the dazzling promise of the SeaCURE project, reveal the specific biological threats it could pose to everything from plankton to shellfish, and ask what this means for the future of geoengineering our own planet. The story starts with an idea as brilliant as it is simple. For decades, scientists have understood that the world's oceans are the single largest carbon sink on Earth, having already absorbed a massive portion of the excess carbon dioxide we've pumped into the atmosphere. So, the thinking went, why not accelerate that process? Why not directly pull that dissolved CO2 out of the water, lock it away safely, and allow the ocean to naturally absorb even more from the air to regain its equilibrium? This is the mission of the SeaCURE project, a joint effort by brilliant minds at the University of Exeter and the Plymouth Marine Laboratory. Their technology, a form of direct ocean carbon capture and storage, or DOCS, is truly cutting edge. Earlier this year, they launched their very first pilot plant, a gleaming testament to human ingenuity located at the Sea Life Centre in Weymouth, UK. Picture this, a complex network of pipes, pumps, and membranes humming with a quiet power, drawing in the very water that houses the center's marine life. This facility is a beast. It is capable of processing a staggering 3,000 liters of seawater every single minute. That's the equivalent of a large swimming pool every few hours. In doing so, it can successfully remove around 100 tons of carbon dioxide from the ocean every single year, equivalent to the work of thousands of mature trees. The process itself is a marvel of chemical engineering. It uses a technique called electrodialysis, which sounds complex but can be thought of simply. Imagine using a powerful set of electric fields, like specialized magnets, to pull specific ions out of the water. In essence, seawater is pumped into the system, where these electrical charges create an acidic environment in one chamber. This chemical shift causes the dissolved inorganic carbon within the water to be released as CO2 gas. This gas is then captured, ready for permanent storage deep underground. The now carbon-depleted seawater isn't just dumped back. To avoid sending a plume of acidic water into the ocean, which would be an immediate environmental disaster, it's treated with alkaline chemicals, such as sodium hydroxide, to neutralize it before it's returned to the sea. On paper, it is a perfect, elegant loop. A victory for science, a beacon of hope in the relentless fight against climate change. But just as the world was preparing to celebrate this remarkable achievement, the scientists behind SeaCURE themselves dropped a bombshell in the form of a new study, and its findings paint a deeply troubling picture. The lead author of that study, Guy Hooper, put it bluntly, "Our ongoing work shows that DOCCS technology is potentially a very powerful tool, but further investigation on the biological effects is now urgently needed." The problem isn't with capturing the carbon. The problem is what happens to the water that gets sent back into the ocean. The study identified two major, potentially devastating impacts. First, the process, by its very nature, removes dissolved inorganic carbon from the water. To us, that might sound like scientific jargon, but to marine life, it's the equivalent of removing air from our atmosphere. This form of carbon is absolutely essential for life to exist in the ocean. Let's trace this potential disaster from the bottom up. Phytoplankton, the microscopic green drifters, are the foundation. They are the grass, the wheat, the race of the sea. They bloom in their trillions, creating more than half the oxygen we breathe. They require dissolved inorganic carbon for photosynthesis, the very process that allows them to convert sunlight into energy. When they can't get enough of it, these blooms fail. The water becomes clearer, but it's an unnerving, sterile clarity. Next up are the zooplankton, tiny animals that graze on the phytoplankton. Their numbers plummet. This means the small fish, the sardines and anchovies that feed on zooplankton, now face starvation. The entire system begins to shudder. But it gets worse. This carbon is also the fundamental building block for the shells and skeletons of countless creatures. Shellfish, like oysters and mussels, and crustaceans, like crabs and lobsters, all depend on it to build their protective homes. Returning water that is barren of this vital element could make it impossible for them to grow, or even cause their existing shells to weaken, a condition akin to osteoporosis in humans. For a crab, a weaker shell means a death sentence during its vulnerable molting phase. For an oyster reef, a critical habitat for countless other species, it means a slow, crumbling decay. It's a recipe for an invisible famine, a silent crisis unfolding at the microscopic level with gigantic consequences. The second major threat comes from the neutralization process. The treated seawater returned to the ocean has a significantly elevated pH, meaning it's more alkaline. For marine organisms that have evolved over millions of years to thrive in a very specific, stable chemical environment, this sudden change is like a chemical whiplash. The study warns that this elevated pH can place immense physiological stress on certain creatures. This isn't just a feeling of being uncomfortable. Physiological stress means their internal bodily functions, their metabolism, their ability to reproduce, their immune systems, are all thrown into chaos as they struggle to cope with the alien water chemistry. Let's be very clear about what this means. A fish's gills are exquisitely sensitive membranes designed for a specific pH balance, allowing them to extract oxygen from water. A sudden shift to more alkaline conditions can damage these delicate tissues, making it harder for them to breathe. It's like forcing an athlete to run a marathon at high altitude with no time to acclimatize. Furthermore, the earliest life stages are often the most vulnerable. The eggs and larvae of many marine species are incredibly sensitive to chemical changes. An alkaline plume could be a lethal barrier, preventing spawning or killing off the next generation before it even has a chance. Guy Hooper elaborated on this, stating, "It's clear from our lab-based experiments that returning treated, decarbonized, and high-pH seawater to the ocean without sufficient dilution could place stress on certain marine organisms. This is a truly sobering discovery, a critical reminder that there are no simple shortcuts or easy fixes in the complex fight against climate change. If you believe this kind of rigorous, self-critical scientific investigation is crucial for our future, take a moment to hit that like button to show your support for the researchers who are brave enough to ask these incredibly tough questions about their own work. The most terrifying aspect of these findings is the question of scale. The pilot plant in Weymouth, while impressive, is a drop in the proverbial ocean. To make a meaningful dent in global CO2 levels, we would need to remove not hundreds of tons, but billions of tons of CO2 per year. Simple mathematics reveals the terrifying scale of the challenge. To remove just 1 gigaton of CO2, you would need 10,000 plants identical to the one in Weymouth, all operating around the clock every single day of the year. The amount of coastline required for the intake and outfall pipes would be staggering. The energy needed to power this global fleet of decarbonization machines would be astronomical, raising the critical question of where that energy would come from. If it's not from 100% renewable sources, the entire endeavor risks becoming a self-defeating paradox, burning fossil fuels to power a machine that cleans up the mess from burning fossil fuels. The potential for cumulative damage is immense. A small, diluted plume of treated water from one plant might be manageable, but vast coastal regions serviced by fleets of these facilities could see their fundamental chemistry permanently altered. We could be creating vast, strangely altered seascapes, hostile to the life that once thrived there. This is where the debate between techno-optimism and the precautionary principle comes into sharp focus. Do we charge ahead, confident we can fix any problems that arise? Or do we proceed with extreme caution, recognizing that we are meddling with a planetary life support system we do not fully comprehend? This is precisely why the SeaCURE team is now urgently calling for a pause and for more research. They have identified critical areas that need immediate investigation. They need to conduct more laboratory studies to see exactly how specific, key marine organisms respond to these discharge conditions over time. Even more importantly, they need to understand the long-term, cascading impacts on entire marine food webs. What happens when the plankton at the bottom start to disappear? How does that affect the fish that eat them, the larger predators that eat those fish, and ultimately the coastal human communities that depend on healthy oceans for their food and livelihoods? This isn't just about protecting ecosystems, it's about responsible innovation. Paul Halloran, another co-author of the study, highlighted this perfectly. He said, "Understanding potential environmental risks is crucial not only for protecting marine ecosystems, but also for supporting licensing applications, developing mitigation strategies, and ensuring public acceptance of these technologies." In other words, you can't roll out a world-saving technology if the public believes you're poisoning the oceans to do it. You need a social license to operate, and that license is built on trust, transparency, and a complete understanding of the risks. We have been here before. In the mid-20th century, chemicals like DDT were hailed as miracles that would end malaria and boost crop yields. Only decades later did we discover their devastating impact on ecosystems, particularly on birds of prey like the bald eagle, pushing them to the brink of extinction. This history serves as a humbling lesson. True, responsible innovation demands not just short-term lab experiments, but long-term, multi-generational studies that track the subtle, cumulative effects on an ecosystem. The team is now pivoting to conduct these vital environmental impact studies. They're engaging with the public, with fishermen, with other marine users to build a consensus on what level of risk is acceptable and how to move forward. This means holding town hall meetings, presenting data transparently, and genuinely listening to the concerns of people whose livelihoods depend directly on the health of the seep. It means co-designing monitoring programs with local communities to ensure that everyone trusts the data being collected. The future of our oceans, and perhaps our climate, could very well depend on the next steps taken in these labs and in these community meetings. To follow this critical story and get updates on other environmental breakthroughs and challenges, make sure you are subscribed and have those notifications turned on. You truly will not want to miss what happens next on this journey. So we find ourselves at a profound crossroads. We have a technology that offers a tantalizing promise, a direct, mechanical way to undo some of the damage we have inflicted upon our atmosphere. Yet that same technology carries a dark threat, a potential to inflict a new kind of damage on the very oceans that sustain life on Earth. The story of SeaCURE and DOX is not one of failure, but one of immense responsibility. It is a testament to the integrity of the scientists who are willing to sound the alarm on their own creation, prioritizing caution over accolades. It is a powerful rebuttal to the idea that technology alone can provide a clean, simple exit from our climate prediction. It serves as a stark and powerful warning for the entire field of geoengineering. Every grand solution we devise will carry its own weight, its own unintended consequences, and its own profound risks. The story of SeaCURE is therefore more than a story about a single machine. It's a parable for our age. It's about our relationship with the natural world, and the immense hubris in believing we can finely tune the intricate machinery of the biosphere without causing it to break in unexpected ways. The ultimate question, then, remains hanging in the balance. Can we truly engineer our way out of the climate crisis without causing irreparable harm to the intricate, beautiful, and fragile planet we are so desperately trying to save? The answer is yet to be written, and the whole world